So before get into our main business, we will try to review quickly some of the selected techniques which are very basics to understand for this probability course. Okay, such as basic counting principles, and there are permutation, combination, and at the end that sets. You all are familiar with all these three things. Okay, so we are going to work out some number of examples based on these topics, so that your basics will brush up here. Okay, and if you have any query or any doubt at any place, so please do, raise your hand, put your comments or put your doubt in your chat box, and try to address it. Okay, so basic counting principles, permutation, combination, of sets, so that we are going to done. So let's start with one example here. Okay, so the example is as follows. It's a small community consisting of men, and each of whom has 2 children. So if one woman and one of her children are to be chosen as mother and child of the year, how many different choices are possible? So if you denote each woman by W1, W2, and so on W12, so each W1 is followed by either C1 into C2. Similarly, so C1, C2 are her children. So you can combine W1, C1, W2, C2, W2, C1, W2, C2, and so on. So there are how many number of different now choices are possible is each woman has 2. So 1 into 2 plus 1 into 2 plus 1 into 2 and so on, 12 times. So that is going to be 12 into 2. So there are number of possible different choices are 24. Okay. So similarly, let's try to, so these are simultaneous tasks here. So that's why here, so product rule. Okay. So 1 into 2 plus 1 into 2 plus 1 into 2 and so on. Okay. Right. So that's why here product and sum rule are both are placed here. Okay, right. Let's have another question here. Suppose a person has 3 shirts and 5 ties. How many ways he can choose a shirt with a tie? So he want to go in a party. Okay, so he will look into the mirror. How many number of possible? So you can denote shirts are like S1, S2, S3. So each has 5 choices, 1, 2, 3, 4, 5. Okay, you can name them T1, T2, T3, T4, T5 by ties. So 1 into 5. So, right? So that's 1 into 5 plus 1 into 5 plus 1 into 5. So there are 3 into 5. There are total number of, you can choose a shirt with a tie T. Okay, right. So what is happening is here is simultaneous task is happening. Okay, so instead of this 1 into 5, 1 into 5, you can simply go with the 3 into 5, because 3 are alike and 5 are alike. Okay, so but you are going to choose out of them only 1 from alike one. So 3 from 3 shirt you are going to choose 1, and 5 tie you are going to choose 1. So you are going to match it. So there are going to be 3C1 into 5C1. That's going to be 50. Okay, right. So what this rule says is, suppose 2 experiments E1 and E2 are to be performed in order or simultaneously. So the simultaneous task means immediately after that. Okay, so with N1 possible outcomes for E1 and N2 possible outcomes for E2, then together there are how many number of possible outcomes of 2 experiments are going to be N1 into N2. So you can go back and check for the first example we were having. So 2 experiments from women, that's W, and E2 is your children, number of children. So N1 possible outcomes. So 12 possible women are there, 12 women were there, and 2 children were there. So then together there were 12 into 2, that is 24. Similarly, for the next case, 3 shirts with 5 ties. Okay, right. So that's going to be, that answer is 50. So this can be certainly generalized to, this is not only limited to 2 tasks. Okay, 2 tasks are performed randomly. Okay, it also can be generalized to finitely many number of experiments. Okay, so how will you generalize this? So suppose here there are n number of experiments, E1, E2, E3, E4, and so on, En. They are to be performed in order or simultaneously with the possible outcomes. So if you refer each one, let's say N1, N2, Nn, capital N1, capital N2, and so Nn. So then together there will be the product of their possible outcomes will give you the possible outcomes of all those n experiments. Okay, right. So this is what is there. If n experiments, E1, E2, En are to be performed in order or simultaneously with possible number of outcomes N1, N2, Nn respectively, then together there are N1, N2, Nn possible outcomes. So these are dot here is product. Okay, N1 into N2 into and so on Nn are possible outcomes of n experiments in given order. Okay, so we have done 2 examples for this. Okay, right. Now let's look at this question now. How many 8 place license plates are possible if first 4 places are to be occupied by alphabets and last 4 by numbers? So there are 8 places, 1, 2, 3, 4, 5, 6, 7, and 8. There are 8 places. Now it is given that first 4 places are to be occupied by alphabets, means A to Z, and last 4 by numbers. So these last 4 by 0 to 9. Now, so how many 8 place license plates are possible now? So A to Z. So here it is not given that you cannot use, suppose here you have fixed A. Suppose you start with A. So the next entry also could be A or B, C, D, anything Z in Z. Similarly here also, all 4 can be A. All are A. Okay, here all are 9, could be possible 9, or all are 0 as well, could be possible. Okay, so they are not fixed. So each place has how many number of, so each place you can treat them as experiments. So each place has this, up to these 4 places has A to Z. How many number of alphabets are there? 26. So 26 into 26 into 26 simultaneous task. So 26 into 26 into 26 into 26 for first 4 places. Into, for the last 4 places, you have each one can be repeated, cannot be repeated. It can be different, can be repeated one, or in other words, identical one. So there are 10 numbers. So into 10 into 10 into 10 into 10. So there are total number of possible outcomes are 26 to the power 4 into 10 to the power. So total number of license plates are possible is this much. Okay, right. So now suppose, so these are here simultaneously happening. Okay, because you cannot leave the plate without filling all these at 8 places. Okay, so you keep in mind that, so if you make some conditions here, okay, then somewhere you can with that then it may not be possible, like it means all the cases cannot be treated as simultaneous tasks. Suppose at least 3 alphabets and 4 means like 5 numbers, something like that. If at least 3 is there, so there would be at least 3 alphabets, 4 alphabets, 5 alphabets, or all could be also possible alphabets. So each case need to be treated separately. Okay, all the cases are simultaneous tasks. So here there is no product sum rule here, so only product rule is there. Okay, right. So repetition of letters and numbers is not permitted. Suppose it is given to you. Repetition of letters and numbers is not permitted. So you have the first place has 26 choices, and second place has now 25, third place has 24, 23, right? Because out of the repetition of letter is not allowed. So if A is used here, A cannot be used again. So only remaining is 25. If B is used here, B both cannot be used here and here. So and so on. The last four places, so numbers are repetition of numbers also not permitted. So you have this is first is 10 place, 9, 8, 7. So all are with dot here. These are not decimals, please. So these are dot product. Okay. So that will be a number of possible license plates if we are going to fix with this condition. Okay. Right. Okay. Now let's get into this permutation and combination, how we are going to handle them. So let's take one or two examples from there as well. Okay, right. So this is example number 5. Okay, so consider collection of 3 novels by authors. Let's say the authors are A, B, and C. So for novels, okay, 2 mathematics books by authors D and E, and 1 physics book by author P. How many arrangements are possible if the books are to be distinguished by the authors? Okay, so you are going to distinguish by the author or author, and you are going to place in a suppose cupboard, okay, in a rack. So how many a number of ways? So it is distinguished by the author. It may not be means like all first 3 are mathematics, and then second is then novels, then physics. They're not like any order here. It's like all mathematics will be together, novels will be together, or physics will be together. Okay, there is no condition. Okay, so what will happen? So there are total 3 novels, 2 mathematics books, and 1 physics book. So total number of books are 6. Okay, so now means there are, you have to fix 6 places, 1, 2, 3, 4, 5, 6. Okay, so if you distinguish by author only, so it may be A, B, C, D, E, P, or maybe any other combination, B, C, A, D, E, P, and so on. So the first place is having 6 choices, right? It can be anyone, A to E or P. Then the second place will have 5 choices. Then third place will have 4 choices, 3, then 2, and then 1. And they are simultaneously happening. So that is 6 into 5 into 4 into 3 into 2 into 6 factorial. So here order doesn't matter, right? Order is not matter. Its only matter is see. Once you fix this place, it is not possible to repeat it here. So obviously, because one book is fixed, but one place you cannot repeat it again. Because only they are limited only. 3 novels are there only. Okay. And they are authored by A, B, and C. Okay, so there are possible is 6 factorial. Okay, so in other words, if you 6C1 into 5C1 into 4C1 into 3C1 into 2C1 into 1C1 also. Okay, so how many arrangements are possible is 6 factorial. That is that we can write some number 720. Okay, right. Now, let's say how many arrangements are possible if the books are to be distinguished by the subjects. Okay, means wherever the books are starting with mathematics, then mathematics should be line up. Wherever it is started with the novels, they are going to be line up with novels only. Means all 3 novels should be sitting together, all mathematics books sitting together, or physics book is sitting together. So if you suppose there are, so there are how many novels are there? Suppose you are fixing 3 novels. right? So 3 factorial ways you can fix first 3 places. Okay, into now how many mathematics books are there? 2 mathematics books are there. So that is into 2 factorial into, then 1 physics book is there, 1 factorial. So if you fix, this is a fixed one, 3 factorial into 2 factorial into 1 factorial. So first 3 place as having choices here, 3 into 2 into 1. Then you have mathematics books into 1. Then you have physics book. Okay, so it's a first, then this is a fixed. Okay, now you can order now. Okay, you can vary now. Means like this mathematics would be after this first mathematics, then novel, then first mathematics, first then physics, then novel, and so on. So how many number of ways such possible cases are there? There are 3. How many type of books are there? Novels are there, mathematics is there, physics is there. So how many number of ways it is possible is 3 factorial. So 3 factorial number of cases are there. Okay, that will be aligned with this. So that's going to be product with this. So that is going to be 72 for this. Right? Okay. To distinguish by the subjects, so number of cases are 72. If you not distinguish by the subjects, only distinguish by authors, there are cases are 722. Sorry, 720 possibly. Right? Okay. Right. So what is happening in permutation and combination is, if the order is important, the number of arrangements of an object is n factorial. So we have seen already. So their order is important. If you are the case of authors, right, order is important here. That's why it is, that is why it's going to be 6 factorial here. Yeah. So one is asking how it is 72. Okay. So see here. Like suppose this is, see what is it is asking in this example is asking how many arrangements are possible if the books are to be distinguished by the subjects. Okay, so there are 3 subjects. So novel, mathematics, and physics. Okay, right. So novel can be arranged in a 3 factorial ways. Mathematics can be arranged in 2 factorial ways, and physics can be arranged in 1 factorial way, because they are going to be line up. Okay, so when a novel is there, suppose one novel is there, all the novels are there sitting in the neighborhood of it. Because if mathematics is there, all the they are going to be together. Okay, so if you fix this order, suppose NMP. Okay, so NMP means 3 factorial into 2 factorial into 1 factorial. These are simultaneous tasks. Now plus. Now another possibility is MNP. That's one more possibility. That's the same thing. That's going to be 2 factorial into 3 factorial into 1 factorial. Now another possibility is, sorry. So another possibility is PNN. And so on. So these are varying now. Okay. So these are how many ways it can be varies. So that much number of sum you will find. Okay. So there are now, see, there are 3 numbers. So 3 into 3C, right? So you can choose, right? 3. The first place is having 3 choice, and fixing first place is for novel. Second place is going to be, you can have, this is going to be M. The third place has so this first place is 3 choices into 2 into 1. So there are number of plus number of time it will happen. You're going to get the same thing here, but number of time it is how many? 6 times. Six number of possibility are there. We are going to arrange this NMP, MNP, PNM, NPM, and so on. Okay, did you get it now?
Yes, sir.
Okay, fine. So there six number of such possible cases. So that's why it is 3 factorial into, so 3 factorial because of this 3 into 2 into 1. So this first place, second place, and third place for the, due to this condition that you are distinguishing by the subject. Okay, right. So if the order is important, then number of arrangements of an object is n factorial. That's what's happening in the first problem. Okay. Now, if the order is not important, so means number of arrangements of n objects you are going to try to identify, where n1 are alike, n2 are alike, and nr are alike, such that n1 plus their sum is going to be the total number of objects. Okay, so out of n, there are n1, n2, and so on, nr. Those are identical. Okay, for example, you have the tournament. Okay, so some Olympic is there, or some particular tournament like tennis is there, chess is there. Okay, so there are, it's like Indians, South Africans, Australians. So they are alike. Okay, means you are from India. So all Indian competitors are falling into the same category, and so on. So here order is, somewhere it is order is not important, somewhere order is important. So depends on the problem individual. So in this case, when the order is not important, then number of arrangements of an object is going to be given by this formula, n factorial divided by n1 factorial, n2 factorial, and so on, nr. Okay, so you will get the answer soon by looking at some example now. Okay, right. So let's talk about this question now. So a tournament has 9. This is competitors. Okay, this is the competitors. Okay, you can competitors. Okay, 3 from India, 2 from Japan, and 4 from Australia. Okay. Now, results of the tournament are announced by nationalities of the players in the order. Okay, it doesn't matter, means like you are Madan Mohan or you are Ching Chong Chu or somewhere. Okay, means like Smith is there. It doesn't matter what title or what name you have. Okay, so what matter is nationalities here. Okay, so the results of the tournament are announced by nationalities of the players in the order in which they are placed. How many such lists are possible? So total number of competitors are 9. Okay. So out of them, 3 from India, 2 from Japan, and 4 from Australia. It is immaterial to talk about what is the order of Indian, those Madan Mohan or some Mrityunjay or somewhere. Okay. Okay, or Sunil Kumar or Sushil Kumar. Okay, so there are 3 alike people, 2 alike, and 4 alike. So how many numbers of such lists are possible is n factorial divided by 3 factorial into 2 factorial into 4 factorial. Right? So total 9 number of list, 9 number of stages are there. So out of this many numbers of pairs are immaterial, so that is why they are going to divide it, and you are going to get the number by following this. Okay, and by solving this, you are going to find that this is going to be in total is 1260. Right, now in a collection of n objects, in how many ways can we select our objects? Okay, so in a collection of n objects, in how many ways can we select our objects? So if the order is important, then it means there are 2 possibilities. Either order is important or not important. Other thing is, it may be possible that replacement is there, or it may not be possible if replacement is not there. So if replacement is there, suppose replacement is there, it's like means once you draw, then you are going to replace it, then you are going to again R. So at every time what happens is, so then in case so you are going to select R objects. So each place is having R n choices. So n into n into n into n. and so on are types. So there, if you talk about with replacement, it means you cannot, you have is important, doesn't not important, doesn't matter. Okay, right. So there are total n to the power r if we are with replacement. So you are talking about now without replacement. So if the order is important, okay, then you are going to have n factorial divided by n minus r factorial. That is given by that is known as the permutation and PR. Okay, right. Now, if the order is immaterial, then you have each has R choices. Okay, so NCR ways. If you go back and check your combination, so NCR and is given by the formula is n factorial divided by R factorial into n minus R. So you soon will be realized, okay, by looking at some examples, how these are going to be placed. Okay, so let us look at some examples for this. Now, let's take this example. A jury of 7 is to be formed from a group of 30 people. Okay, so 30 people group is there, and you want to create a jury of 7 people. So how many different juries can be formed? So in now these people, it may so some of them may be men, some of them may be women. Okay, so for jury we are going to assume that means we are going to look at the only mature people, like above 20 or something. Okay, we can assume that man and woman we can distinguish, but it doesn't matter whether how many men are there or how many women are there. Okay, so here order is immaterial. In how many ways you can place the different type of juries is going to be 30C7. So here order is immaterial, so that's why 37. Okay, right. Now let's look at another problem, that in the same problem, in the case the group of 30 people consists of 10 women and 20 women, 10 women and 20 men, and it is required that 2 women and 5 men should form jury. So how many juries can be formed? Right? So how will you deal with this? Now, so in the case the group of 30 people, so you have 10 women and 20 women, 10 women plus 20 men. So it is required that 2 women and 5 men. So out of 10, 2 women can be chosen, but jury is still formed. So it's a simultaneous task. So into out of 20, there should be 5 men. So this is going to be, there are going to be number of juries can be formed in such fashion. So here in women, it is order is immaterial. Okay. Similarly for men also. So that's why here C. Okay. Right. So that's going to be somewhere in number is something like 6,97,608. You can calculate by calculator. Right? Okay. Okay. So now we are in position of defining the set now. Okay. So a set is well known. It's a collection of well-defined objects, which we call as elements, okay, or objects as well. Okay. So it should be a well, the elements of the set should be a well-defined. Okay. For example, means you can decide the set of students who are scoring the A grade and B grade. Okay. Certainly, you can find out the some relation well defined as there. But suppose you want to talk about how many number of good students are there or how many number of bad students are there. It is undefined, you can't define. So there should be some parameter, should be fixed. Okay, then only you can talk about the collection of well-defined objects. Okay, right. So a set is a collection of well-defined objects or elements. So I hope you can able to distinguish between the well-definedness or it is not well-defined. Okay, right. So here is a set operation. So we are just starting with the universal set, or sometimes it is also known as abstract. So I hope you all are comfortable with these notations now. Omega. Okay. So subset, we say that a set A is called the subset of B when if you have every element of A is inside the element of B. We don't know about the how B behaves, means whether every element of B is also an element of A, then the situation may be different. Okay. So if there is an element in B which is not in A, then you will say that A is a proper subset. Okay. So then in that case, you are going to make it with this here, that cross sign here, with, because it says that proper subset. Okay. So it's A is a subset of B, or we can also say that B is a superset of A. Okay. Right. Equality. So two sets A and B are said to be equal. We denote it by A is equals to B. If and only if A subset of B and B subset of B. This is very clear. Every element of A lies inside B, and every element of B also lies inside A. So then you will say that the both are equal. Okay. Complementation means the complement means outside of the set. Okay. So let A is a subset of the universal set. Then the complement of set A is nothing but the set of all elements which are the part of the universal set but not inside the given set A. Okay, right. So the complement of set A, which we are going to denote by sometime A bar, add with A superscript with C. Okay, AC. C is not the complement. So is the set containing all elements from the universal set but not from the given set A. Then we say that it's a complement. Okay. Now union. So the union of sets A and B, denoted by A union B, is the set containing of all elements in either A or B or both. Okay. So in the set notations, this A union B is equals to X, such that X belongs to A or X belongs to B. So X belongs to here, that omega, that complete set, universal set. Okay, right. Similarly, you can decide the intersection. So A intersection B is the set of all points in the set A or elements in omega such that X belongs to A and X belongs to B. Both. Okay, then you will say A intersection. Null or empty set. So for the conventions of time, or we can say the set containing no elements is called the null set or empty set, which we denote by standard notation is P. Okay, right. Now we will say two sets are mutually exclusive or disjoint when their intersection is empty. Okay, so two sets A and B are called disjoint or mutually exclusive if A and B, A intersection B is equals to P. So sometime you will also see, I may read A union B is A or B, and A intersection B as A and B as well. Okay, there is nothing bad about it. Okay, so you should be able to follow that. Sometime it happens A and B, A intersection B means A and B both we are together. Okay, right. Now the very important law which is going to be is like part of the set theory is known as De Morgan's law, and which can be understood by using the Venn diagram. Okay, so I'm not going to deal with the Venn diagram here. So this is a very much proof can be given by using Venn diagram, so you can do that. Okay, so it says that A union B complement is A complement and B complement. Okay, so let me give you a one Venn diagram. Okay, so let's say this is A and let's say this is B. Okay, right. Now A union B is this full, right? This one is there, A union B. So A union B complement is what? A union B complement is this one. Right? A union B complement is outside this. This is your omega. Now, what is A complement? So, if you are going to look at A complement, this is A complement. So, I'm talking about this is A and this is B. So, A complement is this. Okay, let me use some A. This is B. Let me use these things. Maybe you may be able to distinguish. So this is A complement. Where are these black lines are there? What is B complement is? This is going to be B complement. Okay. Now, if you take their intersection, you will nothing but it will be obtained like A union B bar. Okay. These blue lines only will cover all these things. Okay. Similarly for the next case. Okay. Right. So you can simply you can also generalize to the finitely many or A union B union C. Okay, distributive law is also there, so I must write that. Okay, so distributive law is A union B and C, left distributive and right distributive. So A union B and A union C. So you can distribute union onto both and then take the end. And this is A intersection B union C. All these things you can verify by Venn diagram. A intersection B union A intersection C. Okay, so these are the basic things required for defining the probabilities and so on. Okay, right. So now we are in position of defining the probabilities. Okay, so now there are when you perform an experiment, okay, there are two possibilities. Either you can certainly tell about it, tell about the what is going to come, or you may be able to predict, but you can't tell exactly that is the only thing. It means somewhere the possible outcomes are fall into a certain set. Means like what's called this universal set. Okay, means you have a universal set and you can tell the universal set from where the number is coming. Okay, okay, there are two things, right? Okay, so deterministic experiment is the certain experiment. Okay, and indeterministic means predictable. Okay, you can predict the possible outcome. Okay, but cannot be certain about it. Okay, so for deterministic experiment, what you can take an example is you have a set of white balls. Okay, and you want to draw the ball, 5 balls from them. And what is the probability that all of them are white? Is 1. What is the probability that all of them are red? 0. What is the probability that at least one of them is red? 0. And so on. So this is deterministic environment when you don't know that all in the box, all the balls are white, all the colors you know. But on the other hand, if you mix up, somebody is mixing somewhere white color with red ball, red color with also with some blue and black and so on. Some mixed 7 type of colors are there. So all type of colors are mixed. Then there is a challenge. So such type of environment is known as indeterministic environment. Okay. Now when you perform an experiment, okay, so that's a very fundamental requirement that we are going to use is that conditions should be identical. Means like environmental conditions. Means like when you are throwing a coin or throwing a dice. Means some of the time, suppose there is a storm is going on. Means in the desert area, you just stand up, and when the storm is coming and you are flipping the coin, that's not a good condition where you can predict that what is going to head or tail if you're rolling a dice or what is going to get. So means the condition should be identical when you perform the number of experiments. Okay, so we are going to adhere with such environment. Means whenever you are performing an experiment, the environment should be identically equal. Okay, that means the conditions are identical. Means the coin is also fair. Means like coin is perfectly made fairly, not biased one. Okay, it is not means like break. Means it does not have any break or some means like some damage on the coin and so on. So we should be assuming all these things are there, and then we are going to perform the conditions. Then we are going to perform the experiment. So such experiment is called random experiment. And if you are going to note down all the possible outcomes of it, then that set is known as the sample space. Okay, right. So here is the which we call as random experiment. So a random experiment is an experiment in which the set of all possible outcomes of the experiment is known in advance. Means at least universal set you know. What is going to be the outcome? You don't know. The second thing is the outcome of a particular trial of the experiment cannot be predicted in advance. Means you cannot predict in advance that, yeah, that's going to be head only. Okay, it is not possible. Okay, means certainty is not there. Okay, now, third thing is the experiment can be repeated under identical conditions. Okay, that's the third and last thing. Okay, means the condition should be fair, the damage not there should with the given device, okay, or coin or a dice or cards with which you are going to play or draw experiment. Okay, so these are other identical conditions. They are all in fair means, not a biased. Okay, then if you send, then the set of all possible outcome of the experiment which you are going to note down, that is known as the sample space. Okay, so the collection of all possible outcomes of a random experiment is called the sample space. Okay, so this space could be possibly countable, could be finite, or could be infinitely also uncountable as well. Of course, I can understand that you can definitely give the finite sample space. For example of finite one is you flip a fair coin. This sample space is either head or tail will consist of only possible 2 outcomes. So that will be certainly either head or tail, finite. What about countably infinite? You can tell. Means you are going to flip a fair coin until head appears. Okay, means there is a chance that first head will be there. So first means then you will stop. Then suppose first tail, then head, then you will stop. First head will, once head come, you stop. Then another possible outcome is TTH. Another possible outcome is TTTH, and so on. So this is a countable but infinite set. So one had, right? How many number of trials are happening? 1, 2, 3, 4, 5, 6, and so on. So you can definitely find a correspondence between that omega and the set of natural number to define that set is going to be countable for that case. Okay. What about the uncountable one? Means like when you can have the sample space omega which is uncountable. Suppose you are on the plane. It's like XY plane. I'm not talking about aeroplane. Okay. So here is X and Y plane, and you consider a unit square. Okay, 0, 1, 1. Okay, this is your universal set. Omega is, you have the unit square 0, 1 cross 0, 1. That is going to be given by that omega. Now, what I'm telling you is the experiment is what? You consider any reason of it, any part of it. Okay, any part of it is like a whole or a part of square and so on. Okay, all possible outcomes. So then in that case, you can see that probability you can assign, means whether you can assign the probability or not, that also will be the question. Okay, right? So you can certainly you can somebody can extract the part of it. So you can certainly when we are going to write the sample sample space of it. Okay, then it is going to be uncountable. Okay, it is not countable. Okay, so there are examples for finite length sample space, countably infinite length sample space, or outcome. Okay, that now just keep in mind. Oh. Right. So let's have this example. Write down the sample space for each of the following experiments. Rolling a dice. So I hope the sample space can be written very clearly. 1, 2, 3, 4, 5, 6. There are only possible outcomes. We are only talking about dice of 6 face. Maybe 8 face dice as well. Okay, you can work with it. Means you can definitely play with this. Simultaneously flipping a coin and rolling a die. So that's means like second case I'm talking about. So head, let's say first come head, then head with 1, head with 2, and so on, head with 6. So these are the pairs along with head, and along with tail, there are number of pairs are T1, T2, and so on, T6. Okay, so total how many numbers of possible outcomes are? 12. Simultaneously flipping a coin and then rolling a dice. Okay, I'm not talking about rolling a dice or flipping a coin. That order here matters. Okay, I'm talking about that. The third is, just now we have talked about coin is tossed repeatedly until a head is observed. Okay, so for that sample space is you have already that head, tail, head, tail, tail, head, tail, 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 head, and so on. Okay, now you can also look at each so if you take any member of the sample space, that we are going to call as event. Okay, so if you take any subset of the sample space here, in this case and this case, that is going to be called as event, and we can definitely associate probability with it. Okay, since that we are going to answer soon. Okay, so an event E is a set of outcomes of the random experiments. That is, E is a subset of omega. Okay, so you take any set of outcomes. It's like if you roll a dice, let's say 1, 2, 3, that is going to be E. Okay, that's certainly a subset of the sample space omega, so it is called as event. Okay, or you take E is a set of all, means outcomes are even numbers, odd numbers, or multiple of 3, multiple of 6, multiple of 9, and so on. Okay. So multiple of 9, there is nothing. So this is a null set. Okay. Right. So then we have the mutually exclusive. So we will say two events are mutually exclusive if they cannot occur simultaneously. Okay, so please to understand that this means set theoretically it is also related. Okay, mutually exclusive. You say that two events are mutually exclusive if they cannot occur simultaneously, E1 and E2 equals to B. Okay. Okay, so means for example, if you are rolling a dice. Okay, so E1 is the event which is getting odd number. E2 is the event which is getting even number. So they are mutually exclusive event because a number can be either be odd or could be even. It cannot be both. Okay, so these events are, if such events are mutually exclusive. So you have the sample space is 1, 2, and so on 6. E1 is odd numbers 1, 3, 5. Then E2 is the number 2, 4, 6, or even numbers. Okay, they are mutually exclusive. Okay, now if you take E3, let me take E3 as multiple of 3, 3, 6. So now E3 is neither mutually exclusive with E1 nor with E2. So it can happen in I, right? Okay, so E3 and E1 is non-empty, and E3 and E2 can also happen together. Okay, E1 as well as is multiple of 3. E1 means odd as well as multiple of 3. It is both are possible. Okay, right. So this is the definition of mutually exclusive. Right. Okay. So now let's try to address the classical method. What we have, you may have already learned during your intermediate. So it is used for random experiments which result in a finite number of equally likely outcomes. For example, rolling a dice. Okay, 6-face die, or drawing the cards from the set of 52 cards. Okay, spade, heart, or diamond, or others. Okay, so it's only limited with the sample space which is finite length. Okay, so this is here if let is omega is this one. Okay, so for E subset of omega, so that it is going to be an event, then mod E. So this is not sometime also. It's not a modulus or absolute value. Okay, so this mod is denoting the length of this set. Okay, or in other words, it denotes the number of elements in E. Okay, then these are called the number of favorable cases. You can see. So when E occurs, means that number of elements fall into this event are called the number of favorable cases. And this omega, these are known as the length of this omega is going to fall as the number of exhaustive cases. Okay, right. So then the probability of an event E is given by mod E by mod omega. Means number of favorable by total number of outcomes. So total number of outcomes are n, so that you can write here n, and now depends is mod. So is it equally? So we are also here try to address that all outcomes are equally likely. Okay, then it means they are not biased one. Okay, right. So an outcome W in omega is said to be favorable to an event E if W belongs to it. So if you go back and with the previous examples, so let me have the omega as a sample space by creating rolling a dice 1, 2, 6. Now E1 is the event getting odd number. E2 is the event getting even number. E3 is the event getting multiple of 3. So then certainly by using this definition, probability of E1, so number of outcomes favorable to E1 is 3 out of 6. So 3 by 6. Probability of E2 is number of favorable outcomes are or even numbers are 3 out of 6. Probability of E3 is number of favorable outcomes divided by number of possible outcomes, a total number of outcomes, that is going to be 2 by 3, 2 by 6. So these are 1 by 2, 1 by 2, and 1 by 3. Okay, right. So this is the classical method. Okay, now this is one example. Suppose that in a classroom we have 20 students born in the same year having 365 days. Suppose that they all are born on different days of the year. Assume that outcomes are equally likely. Okay, so students born in the same year having 365 days. So number of possible outcomes are each can be individual on. Okay, so each can be having 365 and 5 days, right? So there are 365 to the power 25. How many number of students are? 25 students are there. So suppose, so first student is having choices is 364. So 365 or 365 into 364 into 360 into and so on into 365 minus 25 plus 1. Now you can relate with n number of students now. You can start with 365 out of 365 into 364 by 365 into 363 by 365 and so on, because we are given that they all are born on different days of the year. Okay, so this will be the answer to this problem. So this will be the probability for this. Okay, now we are going to add with the addressing after this relative frequency method. Okay, so the relative frequency method is not favorable by many mathematicians, or okay, because of something, so that we will understand. Okay, suppose that we have independent repetition of a random experiment under identical conditions. Okay, now let this Fn of E denote the number of times an event E occurs in the first n try. So let's suppose you are flipping a coin and getting means number of times an event occurs means like n trials are there. Out of n, E is the event occurring number of heads. Okay, in the first n trials. Then the corresponding relative frequency is given by the ratio of this total number of trials were n. Out of them, how many times are head are there? Okay, then with this, then the frequency method attests the probability of an event E by this limit value. Okay, so it pre-assumes that limit exists and it tends to a constant limit. But it does not answer why it happens. Okay, whether it happens in every whenever if you repeat the trial again. Okay, whether it will tends to the same limit. Okay, so there are some uncertain answers. Okay, so that's why we have some modern axiomatic approach of assigning the probability definition. Okay, so that we are going to deal with. So let us have one plot of relative frequency of number of heads against the number of trials in the random experiment of tossing a pair. So if all conditions are met in good way, it's like coin is fair and it is in a good environment and then if you perform the experiment in number of trials are like 600, suppose. Okay, number of heads against number of trials. If you try to identify, try with it at home. Okay, number of 600 time you just flip the coin and get the number of head about means out of it. So it is going to be 10 to the approximately 0.5. Okay, in identical condition. So that will be your exercise. You try to flip a coin. Okay, at 600 times, note it down, and how many times you get the head. Take the ratio of it. Okay, 100 times, 200 times, and so on. Just try to get the ratio and try to see whether it is approaching to 0.5 or not. Okay, right. We are going to close now. Yeah, thank you. If you have any question, you may ask. Which one you want to repeat? This one. See, each student is like, see, first student, suppose you number students like by S1, S2, and so on, S25. Okay, and each one will get the different day. So first student will get 365 choices out of 365 days. The next student, okay, the next student will get, so one day is fixed because they cannot be fall on different same days. So the remaining is 364 out of 365, right? Into similarly 363 divided by 365 possibility, right? And so on. Is that clear? Yes.